Welcome all. Now we are going to discuss Theorem 10.4. For that, we have to know what is an open map. Let x and y be metric spaces. A map f from x to y is said to be open if for every open set E in x, the image f of E is open in capital Y. That is a map f from x to y is open whenever it maps open sets to open sets. Okay, so now we will see the theorem 10.4. The statement is, let x and y be normal spaces and f from x to y be linear. Then f is an open map if and only if there exists some gamma greater than 0 such that for every y element of y there is some x element of x with f of x equal to y and norm x less than or equal to gamma into norm y. In particular, if a linear map is open, then it is surjective. So we will see the proof. We have x and y are normal spaces and f from x to y linear map. We have to prove that if f is open, then there exists some gamma such that for every y there is some x with f of x equal to y and norm x less than or equal to gamma into norm y. Okay. For that, suppose f is an open map first. Then f is open means f maps open sets into open sets. So considering the open set ux of 0, 1, that is the ball with center 0 and radius 1 in capital X. It is clearly an open ball and so it is open in capital X. So the image of this ball under f, that is capital F of ux of 0, 1 is open in capital Y by your assumption. Okay. Also, we know that f of 0 is equal to 0 and f of 0 is an element of f of ux of 0, 1. Okay, because 0 is the center point of that ball and so f of 0 is clearly an element of f of ux of 0, 1. So 0 is an element of f of ux of 0, 1 which is an open set in Y. So 0 is an interior point of that set in capital Y. So by definition we can find an open ball. Of course, a closed ball, that is there exists some delta greater than 0 such that uy closure of 0 delta is fully contained in, that is it is clearly a subset of f of ux of 0, 1. Okay, because 0 is an interior point of f of ux of 0, 1. So we can find a ball which is open and of course closed, fully contained in f of ux of 0, 1. Okay, by the definition of an interior point. Let it be equation number 1. Now consider a non-zero element y in capital Y. Then considering norm of delta y by norm y, we can say that it is equal to delta. That means that element delta y by norm y is an element of uy closure of 0 delta. Because the norm difference of this element with 0 is equal to delta, means that this element is clearly in the closed ball uy closure of 0 delta. Okay, and by our equation 1, this is a subset of uy closure of 0 delta is a subset of f of ux of 0, 1, means that that point is an element of f of ux of 0, 1. And so this element delta y by norm y is equal to capital F of x1 for some point x1 element of ux of 0, 1. Okay, let it be equation number 2. Now let small x be the element norm y into x1 divided by delta. Then clearly x is an element of capital X and f of x is equal to f of norm y x1 by delta, that is equal to norm y by delta into f of x1. What is f of x1? By equation 2, which is delta y by norm y. And substituting this, we can say that this is equal to y. That is f of x is equal to y. Okay, that is x element of x and f of x equal to y. So we have chosen actually an element, non-zero element y in capital Y. So we have found that there is some x element of x with f of x is equal to y. Now we have to prove that norm x is less than or equal to some gamma into norm y. Okay, for that norm x is equal to norm of norm y into x1 by delta, and this is equal to norm y by delta into norm x1, which is clearly less than norm y by delta because norm x1 is less than 1. because x1 is an element of ux of 0, 1 means norm x1 is clearly less than 1. Okay, and so we have norm x is less than 1 by delta into norm y. Choosing 1 by delta is equal to gamma, then gamma is clearly greater than 0, and we have norm x is less than gamma into norm y. So we have proven that there exists some gamma greater than 0 such that for every y element of y there is some x element of x with f of x equal to y, and norm x is less than gamma into norm y. So this is the necessary part of this theorem. Conversely, we have to prove that assuming this conclusion, we have to prove f is an open map. Okay. So conversely, assume that for every y element of y there is some x element of x with f of x equal to y, and norm x less than or equal to gamma into norm y for some fixed gamma greater than 0. Now to show that f is open, we have to show that it maps open sets into open sets. For that, choose an open set capital E in capital X and a point x0 element of capital E. Then x0 is clearly an interior point of E because E is open. Okay, so we can find a ball with the center x0 and radius delta which is fully contained in capital E. That is, there exists delta greater than 0 such that ux of x0 delta subset of capital E. Let y element of y with norm of y minus f of x0 is less than delta by gamma. Let it be equation number 3. Actually, we are choosing y element of y with y is an element of uy of f of x0 comma delta by gamma. Okay, norm of y minus f of x0 is less than delta by gamma means y is an element of the ball with center f of x0 and radius delta by gamma in capital Y. Okay, so actually we are chosen an element y in from this ball with the center f of x0 and radius delta by gamma. Okay, then clearly y minus f of x0 is an element of capital Y, since y element of y and f of x0 again in y. Okay, so we are assumed that for every y element of y there is some x with f of x equal to y and norm x less than or equal to gamma into norm y. Okay, so we are applying this for this element y minus f of x0. Then we can see that there exists some x element of x such that f of x is equal to y minus f of x0 and norm x is less than or equal to gamma into norm of y minus f of x0. Okay, by your assumption. This means that y is equal to f of x plus f of x0, which is equal to f of x plus x0, and norm x is less than gamma into delta by gamma, which is equal to gamma by equation number 3, because norm of y minus f of x0 is less than delta by gamma by equation 3. So we have y is equal to f of x plus x0 and norm x is less than delta. Okay, but x plus x0 is an element of capital E because norm of x plus x0 minus x0, which is equal to norm x, is less than delta, implies x plus x0 is an element of ux of x0 delta, which is clearly subset of E by our assumption. This means that x plus x0 is an element of capital E. Okay, so we have f of capital X plus f of x plus x0 is an element of f of capital E, right? So this means that y is equal to capital F of x plus x0. So y is an element of capital F of E. So we have chosen y from the ball uy of f of x0 delta by gamma, and we found that this y is an element of f of E, means this ball is a subset of f of E. That is, uy of f of x0 delta by gamma is a subset of f of E. Okay, this means that the ball with center f of x0 and radius delta by gamma is fully contained in f of E, means that f of x0 is an interior point of f of E, where x0 is an element of capital E. Okay, so if x0 is an interior point of capital E, then f of x0 is an interior point of f of capital E. This means that every point of f of capital E is an interior point. So f of capital E is open in capital Y. That means f from capital X to Y maps open sets into open sets, means that f from X to Y is an open map. Okay, so this is the proof. also in particular, if a linear map is open, then it is surjective, because if it is open, we have proven that for every y element of y, there is some x element of x with f of x equal to y, means clearly it is surjective. Okay, that is the proof. Thank you.